Chemical changes are happening all around us, all the time, from the food we cook to the phones that power our lives. But have you ever stopped to wonder what's really going on under the hood? Well, today, we're going to pull back the curtain and understand the science behind these transformations.
Think about this for a second. Why does a piece of iron start to rust in just a few days, while the battery in your TV remote can last for months, sometimes even years? Both are examples of chemistry in action, but they're on completely different timelines. And it turns out, the answer reveals something fundamental about how the world works.
The secret is all about looking at chemistry through two different lenses. Think of it like a car race. First, you've got speed, how fast the cars are actually going. In chemistry, we call this kinetics. And second, you've got energy, how much fuel is in the tank. That's electrochemistry. Understanding both is the key to figuring out who wins the race. So let's start with that first lens, the speed of a reaction. This whole field of chemistry, kinetics, is all about figuring out why some reactions happen in the blink of an eye, while others, well, they take their sweet time. The rate of reaction is just the scientific way of measuring how quickly your starting ingredients, we call them reactants, turn into the final products. You can think of it as the miles per hour for a chemical change. And here are two perfect examples. Rusting iron is this slow, creeping process that can take weeks. On the flip side, the reaction inside a fuel cell is almost instantaneous, releasing its energy in a flash. It's the same underlying principle of chemical change, just happening on totally different timescales. So, how can we control this speed? Well, chemists have a few tricks up their sleeves. First up is temperature. Cranking up the heat gives molecules more energy, making them move faster and react more often. The other big one is concentration. Think about a crowded room versus an empty one. In the crowded room, people are way more likely to bump into each other. Same with molecules. The more you pack into one space, the more they'll collide, and the faster the reaction. And this brings us to a huge concept, activation energy. Imagine you have to push a boulder over a hill to get it to the other side. That initial oomph you need to get the boulder to the very top, that's the activation energy. If the hill is really tall, it's a slow, difficult process. If it's just a little speed bump, the reaction happens fast. It's the energy hurdle every single reaction needs to clear. So we've covered speed, but that's only half the story. Now let's talk about energy. Where does the power in a battery actually come from? The answer lies in converting the energy stored inside chemical bonds into a flow of electricity we can actually use. And the hero of this story is the electrochemical cell. It sounds complicated, but it's just the scientific name for something you use every single day, a battery. From the giant one in your car to the tiny one in your watch, they all work on this fundamental principle. And its job is beautifully simple. Take that potential energy that's locked up inside chemical bonds and release it as a controlled flow of electrons. We call that flow electricity, and it's the invisible force that powers pretty much everything in our modern world. So how does it work? Think of it like a water slide. The anode is the top of the slide, where a chemical reaction pushes electrons out, like people starting their ride. These electrons then flow through your device, powering it up. They land down at the bottom, at the cathode, where another reaction is waiting to catch them. This constant flow is what we call an electric current. All right, so we've looked at speed and we've looked at energy. Now it's time for the payoff. How do we actually combine this knowledge to control the world around us? This is where chemistry gets really powerful. Let's go all the way back to our first example, rust, which is a type of corrosion. This is one chemical reaction we definitely want to slow down or maybe stop altogether. It's a natural process where metals slowly get eaten away by reacting with their environment, and it's an incredibly destructive and expensive problem all over the world. So how do we stop it? Using our chemistry smarts. The simplest way is to create a physical barrier, like a coat of paint. But another clever method is called galvanization. Here, we coat iron with zinc. Since zinc is more reactive, it essentially volunteers to corrode first, sacrificing itself to protect the iron underneath. It's like giving the iron a chemical bodyguard. But what if we want to speed up a reaction instead of slowing it down? For that, chemists have a secret weapon, the catalyst. A catalyst is a substance that can massively speed up a reaction without getting used up itself. It's the ultimate chemical matchmaker. I absolutely love thinking about it this way. A catalyst provides a shortcut for the reaction. It doesn't change where you start or where you finish, it just finds a much faster, easier route to get you there, like a secret tunnel through a mountain. And how does it create that shortcut? It goes right back to our hill analogy. A catalyst works by lowering the activation energy. It essentially shrinks the hill, making it way, way easier for the reactants to get to the top and become products. The result? The whole reaction happens much, much faster.
So here's the big idea. By mastering these two perspectives, speed from kinetics and energy from electrochemistry, we gain the power to control chemical changes. We can put the brakes on destructive reactions like rust, and we can hit the accelerator on useful ones that run everything from massive industries to the tiny cells inside our own bodies. And that leaves us with one final fascinating thought. Just imagine if we could perfectly control the speed of any chemical reaction. We could create batteries that charge instantly, develop new medicines in a fraction of the time, or even reverse environmental damage at incredible speed. The possibilities are honestly mind-boggling. So what would you change first?